So thank you, Professor Adre. I'm Jayakrishnan Nair. I'm in the electrical engineering department at IIT Bombay since 2014. I was in fact an undergraduate student here myself. I graduated in electrical engineering 2007, went to Caltech for my PhD, and after a couple of years of postdoc, came to IIT Bombay in 2014. My primary training is in queuing theory. So I work in queuing theory and communication networks uh, rather broadly. But along the way, I have also been interested in a few other topics where tools from queuing, networking, and so on can be applied productively. One of them being uncertainty management in the smart power grid, which is in fact going to be the topic of this presentation. Okay. As I said, this presentation is going to be about uncertainty management in the power grid of the future, which is going to be highly renewable rich, right? So before I get into this topic, let me start off with some very high level background. Uh, So the power grid itself consists, I mean, in the simplest terms, of three different entities, right? So there is generation, there is consumption, and there is a transmission and distribution infrastructure between the two, which basically links the generation to the consumption, right? And one of the main things that the grid needs to satisfy at every point of time to be stable is that the supply must equal demand, right? Instantaneously, the amount of energy generated must be equal to the amount of energy that is consumed. Now, how is it that we have been able to do with this over the last, several decades? The primary reason that we have been able to do this is because there is relatively small supply side uncertainty and relatively small demand side uncertainty. What I mean by that is that since generators have conventionally been, thermal or hydro, well, for example, let's say conventional generators which pollute, dirty as they might be, they are extremely controllable and extremely reliable, right? So that's small supply side uncertainty. When it comes to demand, it turns out that at a reasonable level of aggregation, it is possible to forecast demand really, really well up to a few percentage points of error, for example, 24 hours ahead of time. Right? So you have small uncertainty on the generation side, small uncertainty on the demand side. So matching these two becomes a relatively doable problem. Now, where this will get turned on its head is where we introduce a considerable volume of renewables into the mixture, right? So this is just an illustration. So this plot here shows corresponding to a wind farm. Each of the 30 plots you see on this picture basically shows the amount of power generated out of that wind farm as a function of time, right, across the 24 hours of a day. So you can see that, if you average this across all the 24 hours, that average line looks reasonably flat, but on any given day, the generation can go wildly swinging up and down, sometimes stay flat for days on end, sometimes be very, very variable, sometimes be very low for days on end, and so on, right? So this works just fine if this kind of generation accounts for 1 to 2% of your overall generation portfolio. But if this is to constitute, let's say 30, 50% or more of your generation portfolio, you can imagine that it's going to result in considerable challenges, right? So the big question is, how is it that we should handle the supply side uncertainty that is induced by these renewables? Now, this is a particularly pertinent question for India itself, because we have made some very ambitious commitments about introduction of high volumes of renewable energy in the decades to come. Right? In particular, up to 2030, we have made some very ambitious commitments, as some of these headlines are showing. Right? And it's important that we recognize that this transition has to be done carefully, because we have experience from other countries. Right? For example, about 10 years back, Germany started introducing solar very, very aggressively. And there are reports that indicate that in the first few years of this transition, their greenhouse emissions actually increased rather than decreased. Right? This is in part because of the fact that to be able to deal with the sudden dips of renewable generation, you have to keep standby conventional generation running and idling, right, to pitch in whenever the renewable generation dips. Every now and then you have a scenario where the renewable generation is so much that there is not enough demand to be able to consume that, right? At such times, the electricity price in the real-time markets would actually become negative, right? So the grid is literally paying people money to take the energy away so that it can stay stable. Right? So these are all the kind of issues that one has to deal with when renewable generation forms a considerable part of your generation portfolio. Right? And our approach in addressing these challenges primarily come from what I would call an operations research style of toolbox. So we apply probabilistic models, tools from control, optimization, occasionally game theory to address this question of how it is that this supply side uncertainty is to be managed. So in the past several years, we've been looking at this problem in various dimensions. We have looked at how it is that you should optimally procure conventional generation, given that you have this variable renewable generation also to consume, to be able to use on hand. How do you robustly identify operating points for the grid, given the short-term uncertainties that are inherent in renewable generation? And most recently, we've been looking at this question of how to use storage. How do you size storage and how do you manage storage in order to smooth out supply side uncertainty? So this last bit is what has been recognized as part of this award. So I'm going to use the rest of my time to give the briefest of introductions to what we have done in this space. Right. So when we started thinking about this, the first fundamental question that we wanted to address was the following. So suppose you are given a bundle which consists of a renewable generator, say think of a wind farm, and an associated battery. So imagine that the battery was on site, right, along with the wind farm. Now, this bundle is basically contracted to supply electricity to the grid according to a certain profile. So from the standpoint of the bundle, this basically looks like a demand curve, which this bundle is supposed to satisfy, right? This is conventionally how things are done in practice. A large wind farm would be contracted to supply electricity to the grid according to a certain curve in time, and there would be penalties for deviating from this curve, right? So the basic question we ask is, given this bundle, what is the reliability of this bundle? To what reliability can this bundle actually meet the demand curve that it's expected to meet? And if you flip this question around, another way of saying this, if you decide what reliability you need, then how much of battery storage does this bundle require in order to meet the demand with that target level of reliability, right? And one of our main contributions has been to be able to answer this question using a mathematical model, specifically using a Markovian model, right? So at a very high level, it works as follows. So you have renewable generation, you have demand. We look at the difference between the instantaneous supply and demand. Right? This is what we call the net generation. And our basic model is that the net generation is some function of a Markov process, right? Now, what does that mean? The Markov process will basically capture all of the factors that can influence supply and demand. So for example, the state of the background Markov process would include things like weather forecasts, the time of the day, the time of the year. All of these factors that influence supply and demand are all baked into the state of this Markov process, and the net generation is some function of the state of the Markov process, right? So the power of this model is that it's extremely general, right? It allows you to capture all sorts of dependencies, temporal dependencies, interdependencies between supply and demand, battery ramp constraints. All of these things can really be captured within this one simple unifying model, right? And under this model, we are in fact able to answer very precisely the questions that I had posed before, namely what is the reliability of the bundle and how large a battery does one require in order to meet a certain target level of reliability, right? So I won't get into the details here, but under some conditions, what we can show is that the unreliability of the bundle, which is characterized using this thing called the loss of load probability. This is the fraction of time the bundle is unable to meet the demand profile, right? This loss of load probability can be shown to decay exponentially with the size of the battery. And moreover, we are able to characterize, in terms of our model, the parameters of this exponential decay. So once you have this characterization, you can write like a clean formula that gives you an estimate of how much storage you need in order to meet a certain, reliability requirement, right? Now, this by itself is a contribution, but not particularly significant, because one could always just do some brute force simulation to figure out, how, using time series historical data to figure out how large a battery I would have needed in the first place, right? So I think the real, shall we say, contribution here is that our framework can actually be used to answer even many other interesting questions that are of, and I'm going to give a couple of examples of these that we have looked at. Right. So one of the primary issues with renewable generation is that battery storage remains extremely prohibitively expensive. Right. So one of the questions we asked using the same framework that I've just described is the following. To what extent can you actually save on the amount of battery storage that is required if you're able to share this battery between various sources? So in this picture, what I have is n different renewable generators. If they were to meet their own reliability targets, they would have required their own batteries, right? Battery size B1, B2, B3 up to Bn, right? These have been characterized before. But how would this compare with a scenario where these generators were actually going to share a common battery, a shared battery, which I'm calling BS, right? What is the purpose of this sharing? When you have an instantaneous surplus at one location, that can actually be directly used to meet an instantaneous deficit into the other location without involving the battery so much, right? This is why you would hope that the shared battery size would be smaller than the sum of the individual battery sizes. So that's the question we ask. Is it true that the shared battery size is much smaller than the sum total of the battery sizes in the absence of sharing? And there again, using the same Markovian framework that I introduced before, we can show that in fact, you can show that the shared battery size, if you assume that the net generation processes are independent, statistically independent, you can show that the shared battery size is at most the largest of the individual battery sizes. So you can imagine that's a substantial saving, right? If the battery sizes were comparable, that means that you're talking about n-fold reduction in the size of storage by just sharing the battery between all of these different renewable generators.
Nair,
Right?
2 minutes, please. Yeah.
Yes. So this suggests tremendous economies of scale, but that's based on a theoretical model assuming statistical independence. So the next natural question is, can these kind of economies actually be realized in practice? So we have done a considerable data study to actually show this. This is just one figure I'm showing. So we have taken 4 locations which are about 500 kilometers apart. That's the kind of geographical separation we require for savings that are comparable to what we would get from statistical independence to show. So on the figure on the right, you can see that as you increase the number of locations that are actually participating in the sharing, the battery requirement remains flat, which means that as you bring more and more generators into the picture, the cost per unit generator of storage basically drops drastically. All right. So there are the same framework can also be used to answer other questions of similar interest. So we have looked at the scenario where you have 2 renewable generators. They may have their own individual battery, but they can dynamically help each other by sharing energy. Right. This might also apply to 2 microgrids, which have their own on-site generator, and they can help each other in times of deficit. And we come up with a mechanism for these 2 agents or 2 microgrids or these 2 renewable generators to help each other in a manner that actually provably improves the reliability of both of them. Right? And another thing we have looked at is community storage. So you have different people in the community who have participated and pooled their money to buy, let's say, a common battery. How should this battery be basically used in a manner that is not just efficient, but also fair between all of these players? So that also brings in a game theoretic aspect to all of this. So yeah, that's it. That's all I have for this high level introduction to this work. I will conclude by acknowledging my collaborators on this particular brand of work that I just presented. Vivek Deolkar is a PhD student working with me in electrical engineering who has done a lot of this work, who has driven most of this work, and my other collaborators, Ankur Kulkarni from Systems and Control. So with this, I'll stop. Happy to take questions.